Next, I would like to introduce the basic thing of adders. The full adder is then followed by the circuit design considerations, then logic design considerations, then I will summarize. So in this file, you can see this is a adder, the schematic of the adder, and the full adder has 3 inputs and 2 outputs, right? So 3 inputs include the input A, input B, as well as the carry input. And 2 outputs is composed of the carry output as well as the sum output. So this is a full adder. In terms of half adder, we only have 2 inputs. We don't have the carry input. We only have the A and B inputs. And we have 2 outputs, C out and sum. So this table gives us the truth table of the adder. So you can see A, B, C, A, B, and Ci are inputs, and CO here stands for output. CO output and S output. And from this truth table, we can find out some regularities. So you can see if the input A equals 0 and B equals 0 at the same time, no matter the Ci equals 0 or 1, the C output, I mean the CO, is always equal to 0, right? So in other words, if A and B are both equal to 0, then C out is definitely equal to 0, no matter Ci equals 0 or Ci equals 1. So this is called carry delete, which means the Ci is deleted. And also, you can find out here, when A equals 1, B equals 1, at the same time, no matter Ci equals 0 or Ci equals 1, then CO is always equal to 1. So this is called carry generate state. And between this, we can find out when A is different from B. In other words, when A is equal to 0 and B is equal to 1, or A is equal to 1 and B is equal to 0, so they are different. And at this time, the Ci would be copied directly to the C output. You can find out here, when Ci equals 0, then CO equals 0, 1 and 1, and 0, Ci equals 0, CO equals 0, Ci equals 1, then CO equals 1. So this is called carry propagate. Okay, so we have 3 different things: carry delete, carry generate, and carry propagate. And this file, you can find out the expression for the sum and carry output. So the sum could be expressed as A exclusive B, then exclusive Ci, which is equal to AB bar Ci bar plus A bar C, A bar B Ci bar plus A bar B bar Ci plus AB Ci. This is expression for the sum. And also the CO equals AB plus BCI plus ACI. So this is a very fundamental expression for the generation of the sum and carry output. And also we can, according to the carry delete, carry generate, and carry propagate, we can define 3 new variables which only depend on AB, not depend upon the Ci. So here we define the carry generate signal. G here stands for generate. So G equals A and B. So when A equals 1, at the same time B equals 1, then G is equal to 1, definitely, right? So it's called carry generate. And we also have a definition of the carry delete. So D equals A bar and B bar. So when A equals 0 and at the same time B equals 0, then D is true, right? D is equal to 1. So this is called carry delete or carry kill. And also we have the definition of carry propagate. P equals A exclusive or B, or B equals A plus B. It's called carry propagate. So when A is 1, and B is 0, then P is 1. Or when A is 0, B is 1, then P is 1, right? This is called carry propagate. So according to these three new variables, we have definition of the S, and we can also express the S and C output as a function of these new variables. For example, the CO equals G plus PCI, right? And S equals P exclusive OR CI, because we know that the P equals A exclusive OR B. So if we insert this one into this expression, we can find out we have the same expression as this one, right? So S equals P exclusive OR CI. And regarding the CO, expression of CO, which is equal to G plus PNCI, so we can find out the carry output could be generated at current stage or could be propagated from preceding stages to current stage, right? Here, I like to introduce the 4-bit ripple carry adder. This is a full adder. FA here stands for full adder, and which has 3 inputs: A0, B0, CI0, and also has 2 outputs, CO0 and S0. And if we connect 4 full adders together, one by one, so the first one and C output, CO of the first full adder is serving as the C input of the second full adder. And this is true. Also, the output of this one, CO of this one, is serving as CI of this one. So we have a 4-bit ripple carry adder. So it is called ripple carry because the carry will be transferred from the first one, the first full adder, to the second full adder, the third full adder, finally to the last full adder. Okay? So from this schematic, so what's the critical path of this 4-bit ripple carry adder? So from your point of view, so we know that only after the calculation of this one, and we can get the CO0, right? After that, the full adder of this full adder will take calculation, right? And when we achieve the CO1, and after this, the third full adder could take action of calculation, right? Then this one. So this is actually the critical path of the 4-bit ripple carry adder, from this one to this one, this one to this one. Okay, so this could be expressed as the T adder. I mean, the program delay of the adder is approximately equal to the n-1, n-1, which means, for example, this is the n. We have this one, and this one, n-1 times T carry plus the maximum delay of the T sum and T carry, right? So this one stands for the n-1 T carry, then plus this one plus the maximum value of T sum and T carry. So T adder, you can find over here, is proportional to the number of the stages, number of the bits, right? And here you can find out T adder has a linear relation with the number of the stages or number of the bits. And also from this expression, you can find out it is far more important to optimize T carry, because T carry is multiplied by the number of the bits, right? Then, so it is far more important to optimize T carry than optimizing the T sum, since this one is multiplied by n-1. Okay, therefore the T sum has only a minor influence on the total value of T adder. So this is expression for the 4-bit ripple carry adder. This example, we have the 8 bits, A plus B, and this is a lowest bit, this is a highest bit. Okay, so this is A and B, this is C output, this is sum. So when we take calculation, and we first to add this one and this one, right? This bit and this bit. Then we have this C output, carry output. Okay, then this one could be added by this one. Then we have this output. Okay, and this one, and this one, and this one. So just like a ripple, right? And finally, we can derive the output of the carry output and the sum. Okay, so therefore, if we assume that the T carry equals T sum equals 1 nanosecond, therefore T adder is approximately equal to 4 times T carry, right? 7 times T carry. 1, 2, 3, 4, 5, 6, 7, right? 7 times T carry plus 1 nanosecond equals 8 nanosecond. Okay, so this is an example by using the above expression, this one, to calculate the critical path of the ripple carry adder. And also, I'd like to introduce the inversion property. So if we invert all the inputs to a full adder, we can obtain an inverted value for all outputs. What does it mean? It means if the input is A and B and Ci, and if we invert all these inputs like this, so this is A bar, B bar, and Ci bar. Therefore, the result of the full adder is the inversion of the previous result. Okay? The same is true here if we invert A bar, B bar, and Ci bar. Therefore, we can derive the C output bar. So you can see here, so if this is A, B, and Ci, this is S and C output. And if we invert A and B and C at the same time, then finally we can achieve the C out bar and S bar. Okay? So the circle here, the schematic represents the inverters. So it's the inversion property. So later we will see the inversion property could be used to optimize the inversion, to increase the performance. So we know that the adder is actually the critical module in the data path. Even that we have, I will introduce multiplier next time, but the multiplier is actually composed of adders. So adder is actually the critical module in the data path, which could be optimized in both circuit level or logic level. So I will introduce later.